All right, good morning. Welcome back to Applications of Calculus 2. We are going to be talking about section 11.2, expected value or average. So a couple of definitions first. I'm going to do a derivation for us, and then we're going to do an example that's kind of a long example. So the first idea is the average. Okay, this is the symbol we use for average. This is my mu. Okay, if you were in biology, you probably have mu with a longer tail to it because it's for like micrometers or microliters. My mu looks kind of a combination between an M and a U. Okay, so that's how I write my mu's. And this is expected value, which is E of X. Okay, so expected in probability has a meaning, it has a definition. And this is equal to the integral of X times f of X, again, over its whole domain. Okay, sometimes this is an easier problem to solve than just integrating out f of X by itself. So we're going to go ahead and see how that works. Okay, if you took probability and statistics, expected value, the way we define it in regular probability and statistics, we say expected value is equal to the probability of the, well, let me write it down. The value of the event times the probability of the event. Okay, and then we add all of those up. Okay, so if you took probability and statistics, you learn expected value is value of the event times the probability of the event summed. Okay, add it all up. Now, this is the discrete case. Again, if you're dealing with dice rolls, this is what you're going to end up with. In calculus, with continuous distributions, we're going to have that sum turns into an integral. The value of the event we're going to call x. The probability of the event is your f of x. So your e of x, your expected value of x, which again is your average, is equal to your integral, again, over your whole domain of x times f of x. I like the e of x notation because e of x squared means the integral of x squared times f of x. We're going to see how this is related to variance in a little bit. If you go a third one, okay, this is the integral of x3 f of x. This is related to something called skewness, okay, which is, again, it's a position thing for your distribution. It tells you like how off to one side it sits. And then finally, there is an e of x to the fourth, which is x to the fourth, x. And this is, I'm thinking of spelling, no, it's a u, it's kurtosis. Okay, so this is related to kurtosis. This is not the exact formula for kurtosis, just like this is not the exact formula for skewness. It's just related to it. You need this in order to figure out kurtosis. And this is how fast the distribution drops off of its mean. Okay, so this would be like a high kurtosis, and this would be a very low kurtosis kind of a distribution. Okay, so I know that in one of the economics classes they deal with kurtosis, but I don't know anybody else that uses this. Okay, it doesn't have anything to do with the bad breath of the distribution. Okay, that's a different value. So, all right, that's what the E notation gives us. And it's going to be nice because we're going to figure something out. Because in the book, we have the average, which is equal to integral of f x times f of x. And then they talk about standard deviation. Actually, they don't talk about standard deviation. They talk about variance, which I just pronounced variance. But variance, which is going to be x minus mu squared integral f of x. And we're going to integrate that over its whole domain. Now, I would say you'd have to be crazy to calculate it this way. So there's another formula that we use. And that formula is going to be, I'm going to do a couple of things before we start the formula. I'm going to say, if I just integrate f of x over its domain, remember, f of x is a probability distribution. Recall, if we integrate f of x over its whole domain, what should this integral come out to be? It should come out to be 1. Okay, because its probability distribution has to integrate out to 1. So let's go ahead and multiply this out. So we're going to say this is going to be integral of x squared minus 2x mu plus mu squared, parentheses, f of x. All I did was FOIL this out. That's all that happened. Okay. And now what we're going to do is we're going to break this apart. We're going to say this is the integral of x squared f of x minus 2 mu. And mu is a constant. So we can always float constants through our integral sign. We can't float x's through the integral sign or f of x's through the integral sign, but we can certainly float mu, which is a constant, and a 2, which is a constant, through the integral sign. Okay, and then finally we have the integral of mu squared f of x. Now remembering that mu is a constant, mu squared is going to be a constant. So let's go ahead and write that down. So we have integral of x squared f of x minus 2 mu integral of x f of x plus mu squared integral of f of x. And again, this is all over the whole domain. Okay. Do you remember just before we started, I tried to remind us and say, okay, what is the integral of f of x over its whole domain? And it's 1. So we're going to say this is the, now I don't know what it is for x squared times f of x. I have no idea what that is. Minus 2 mu, okay? And then what we have here for this last term, we have mu squared, and the integral over the whole domain of f of x is just 1. Now, here's a tricky part. What was the integral of x, f of x? Wasn't that mu? Like, yeah, that's mu. So we're going to go ahead and say that this thing here replaces, and it's mu. So we're going to say this is the integral of x squared f of x minus 2. This is going to be mu squared, and we have plus mu squared. Okay. We have negative 2 mu squared plus a positive mu squared. Negative 2 plus 1 is minus 1, right? You owe $2, you pay 1 back, you still owe $2. You still owe $1. So we have the integral of x squared f of x minus mu. And then I'm going to turn back around and I'm going to say, do you remember what the mu is in its definition? We're going to say, mu squared. We're going to have integral of x squared f of x minus mu squared. Isn't this x f of x integral over its whole domain squared? Okay. So going back to the e notation, remember this was e of x squared minus what was x f of x? That was e of x. And then we're going to square it on the outside. So we're going to calculate the mu first, and then we're going to square the whole thing. This is equal to your variance. And because this is all now in integrals, right? I mean, there are different integrals. There's x squared times f of x and then x times f of x. So they are different integrals, but they are all integrals now. This looks like a more calculus type of a definition. Now, to get your standard deviation, okay, what we're going to do is we're going to take the square root of our variance. So the standard deviation is just equal to the square root of the variance. Now, I rate my sigmas as my standard deviation as a kind of a sideways 6, just because I find it easier to work that way. I think most people, when you watch people write a sigma, they'll make a little loop, they'll make an O, and I'll give it a little hat at the top. Mine are a sideways 6, just because I find this to be a little bit faster. If you actually learn your penmanship in Greece, when you learn how to write proper Greek letters, I think you're going to write it this way rather than the way I wrote it. So that's fine. So that's just going to be the square root of e of x squared minus e of x squared. And that's going to be our standard deviation. Okay. So just let me give you one more little piece of what a standard deviation is, what a mean is, just so that you can have an understanding of what's going on here. So physically, the mean is kind of like the center of mass. Okay. It's like if you've got a plate of food right after Thanksgiving, it's very apropos. Where do you put one finger to balance your plate? Do not try this experiment at home. Your parents will kill you. Whoever cooks Thanksgiving dinner will be very upset if you try this experiment. But if you put your one finger right against under that plate, that one spot where you balance it, that's the average. That's the mean. That's the center of mass. Standard deviation. This is moment of inertia. Okay, and you say, well, of course, obviously, yes. And moment of inertia, like I know you have done this experiment in high school because in physics in high school, you do this experiment where you put somebody on like a sit and spin kind of a contraption, or if you see an ice skater, when the ice skater holds her arms all the way out, she's got a high moment of inertia. She spins very slowly. So it's like resistance to spin. If she puts her hands in, then she starts spinning much faster. If you do the sit and spin, and the high school that I went to, we gave a kid two dumbbells, and you held them out, and you spin it, and a kid would spin very slowly with the dumbbells stretched out. But as they pulled the dumbbells into their body, they would start spinning a lot faster. Okay, that's moment of inertia. When you are spinning and your dumbbells are like held all the way out in your hands, your distribution of mass is very high. When your arms are out, when the ice skater's arms are out, her distribution of mass is spread out all over the place, right? You've got a whole bunch of mass all over the place. And the resistance of spin is very small. This is a high standard deviation. A low standard deviation, okay, she brought the dumbbells into her body, or the person brought the dumbbells into his body when he was doing the spin. So the mass is all centered around at the average. They have a very low standard deviation, and they start spinning faster and faster and faster. So that's the idea behind of what a standard deviation is. Mass is measures of center. Standard deviation is a measure of spread. Variation is also a measure of spread. Okay, back to calculus. Okay, so we could do something like that. All right. So let's see here. We have some variations. We have some stuff. All right. So we have a problem, and I'm going to ask you a whole bunch of questions about this one problem just to see everything here. And I apologize for the way that we did this. All right. So things that we can ask you at this point. Okay. So for any distribution that I give you, I could ask you, what's the average? What is the average? What is the standard deviation? Those are probably going to be the two most common questions I will ask. Okay, there's other questions though. We can say, um, what's the probability that the distribution is greater than the average? Okay, we can ask, like, what's the probability that something lands, the probability that a function is greater than its average? Okay. Part D is, what is the probability that we could say, what's the probability that X is within one standard deviation of the mean? Okay. So we can go ahead and do that. So we could say of the mean, and we just want to know the probability that X is between one standard deviation below, one standard deviation above. Again, if you took probability statistics, we have the empirical rule, which deals with the mound-shaped, a hill-shaped distribution. They call it bell shapes because when we were inventing this thing at this time, the way that people told time was there would be these large bells, and they would ring at noon. They would ring at various times over the day so to let people know this is what time it is. So bell making was very important to the people that were coming up with probability and statistics. So when they looked at this distribution shape, they said, "Oh, it's a bell." Okay, we make Christmas cookies now. We don't really deal with bells, but they call it bell shaped because that was important. And if you took probability and statistics, then you learned the empirical rule, and you said 68% of your data is within one standard deviation. of the mean. 95% is within 2 standard deviations. Okay, and 99.8% or 7% rather, 99.7 is within 3 standard deviations of the mean. Now, we're only going to ask you for 1 standard deviation. We just want to know what 1 standard deviation of the mean is. If it's your distribution is bell-shaped, symmetric, then you're going to end up with like, this is going to be a very close approximation to what's going to happen for that. So that's kind of, we're verifying numerically what the empirical rule is. But we're doing it with other distributions because the normal distribution, okay, we can't integrate that. Okay, that's 11.3. We can't integrate it. The function for the normal distribution, I'll just tell you now, is 1 over the square root of 2 pi sigma squared, it's a constant, times e to the negative x minus mu squared over 2 sigma squared. Okay, that's called a Gaussian. Okay, if I pared everything down and made it really easy, just to integrate this, x squared over 2. Okay, again, there is no x on the baseline. There is no u substitution for this. We can't integrate this analytically. Now, we could integrate it in other ways. We could use Simpson's rule. We could construct a Taylor polynomial for this and integrate it that way. And as a matter of fact, that'd be a really good project for this class, is to either come or compare, okay, let me figure out the probabilities for this thing using Simpson's rule, figure out the probabilities using Taylor polynomials, compare the two to see which one is closer to the sheet that is the, or the calculator that will do it a little bit better than we can do it with by hand. But that would be a really good problem. That would be a really good project for this class. But we are not doing that because we have 1 week left. Okay, but that's technically, this bell-shaped curve is this guy here. It's called a Gaussian. But that is what the empirical rule goes to. We could integrate it numerically. Okay, there's a couple of tricks we could use, and then check to make sure all of this stuff works. We will not be doing any of this. Okay, we use a table or a calculator to get these values. We do not do them analytically, which is why probability and statistics is a 100 level class. We don't make people integrate this. Like if you just got out of, algebra and you're like barely hanging on to statistics, I can imagine like, okay, we're going to learn this now. Okay, good luck. Like I couldn't imagine them doing any of that. But technically that's what they're doing. It's just that there's a table of all these values. Oh joy. So we don't have to integrate all of this stuff. Okay, and the people who made the tables went through the Simpsons rule or went through the Taylor polynomials and did it that way. So aren't we lucky that we don't have to do that? On to the example that we have. Okay, we have parts A, B, C, and D. Okay, what is the average? What is the standard deviation? What is the probability that f of x is greater than the average? Okay, what is the probability that that x is between, right? If you throw a dart at your probability distribution, what's the probability that you land between 1 standard deviation below the mean and 1 standard deviation above the mean? Okay. There's actually a third problem that we're going to have here, and we're going to say, what is the median? Okay, and again, if you took the probability and statistics class, the median is the middle point. It's the center point of the distribution. Okay, it's the place where, if we have from A to some number m of f of x, it's where that probability turns into 1/2. Okay, so that we're going to figure this out. So it's kind of like an integral equation where we get to put m in for the upper bound and solve for that. So those are, go ahead and make that an E. So those are the 5 little parts that we're going to go ahead and do for this thing. So my apologies that we're going to start the example now, and it's already been a few minutes into the video. So I picked a pretty tame example, and I said, okay, let's see, where are we with this guy here? We are, find my little page here. We don't want that. We don't want any of that. Okay. I just want to write down the problem as we have it dealt to us. Okay, rather than all my scratch work all over the place. All right. Ah, there we go. That's what I want. Okay. I want this, the function that we have here is the square root of x over 18 on the interval between 0 and 9. Okay. So we know what square root of x looks like as a function. We end up with something like this, okay, between 0 and 9. 1/18th just pushes it down a little bit, but going back to my being able to graph functions based off of translations, okay, graph transformations, 1/18th times the square root of x, we know what this is going to look like. The 1/18th is compressing it. We know what the shape of the square root of x looks like. We end up with something like this, okay? So the first thing that we're going to do is we're going to say, can we figure out what the average for this function is? So yeah, we sure can. We're going to say this is 1/18th, and the value for figuring out the average is x times f of x. Okay, and again, we're going between 0 and 9. We're going over a whole domain. So we have to go back and deal with our rules of exponents. We have x times the square root of x. This is equal to 1/18th. I can move the 18 out of the integral sign. We have x to the 3 halves. This is x to the 2 halves times x to the 1 half. We add the exponents, the x. And we're going to go from 0 to 9. And this is all we have to integrate. So that's not too bad. So this is just 1/18th times x to the, go ahead and do an integral. So 5 halves times 2/5. Okay, and we're going from 0 to 9. Okay, so this looks like 1 over 9. The 2's cancel here, times 1 over 5 x to the 5 halves, going from 0 to 9. So this is 1 over 45. And then we have 9 to the 5 halves minus 0 to the 5 halves. Okay, that's not so bad. We have 1 over 45, 9 to the, what is this? What do I want to do with that? There we are. Okay, so 9 to the 5 halves. Okay, 9 caret to the 5 over 2. Okay, is 243. And this is going to be 243 over 45, right, minus 0. 0 to the 5 halves doesn't really matter. So we're just going to have 243 over, I want 243 over 45 over 45 equals, and we'll just go ahead and hit that, and we'll say this is, where's my little, there it goes. Okay, 27/5. Now this is the average. Okay, we don't have to worry about a probability. The average can be bigger than 1. The average could be smaller than 1, or it could be smaller than 0. If I go ahead and take temperatures in Antarctica, I'm probably going to end up with a negative average. Okay, if we got a whole bunch of people in a room and said, okay, we're going to calculate your net worth, or the average net worth of the class, the people who have mortgages are going to have a very high negative value for their net worth. The average for the class is going to be rather negative because mortgages are expensive. Okay, so that's our average. What about our standard deviation? And this is the reason why I showed you the alternate version for carrying out standard deviation, because usually you've already had to figure out the average. Now, what we're going to do is we're going to get x squared times f of x. Right, this was e of x squared. So this is going to be integral of what we have here. We have 1 over 18 times x squared times x to the 1 half. Now, we haven't done any calculus yet. We've just set up the problem. So we're going to figure out the expected value of x squared. So this is 1 over 18 integral from 0 to 9 of x to the, well, this is 4 halves plus 1 is 5 halves. Okay, So we're set up the integral to figure this thing out. Now we'll go ahead and integrate. So this is 1 over 18. We have x to the 5 plus 2 is going to be 7 halves, and we have 2 sevenths as such. And again, we are going from 0 to 9. Okay, so that's what we're doing. We're just figuring out the e of x squared, and we'll go ahead and do this. And this is going to be 1 over 2 cancels with that 2, so we end up with a 1 over 9 here, times 1 over 7. And then we have our 9 to the 7 halves minus 0 to the 7 halves. Okay, so this is 1 over 63, okay, times whatever 9 to the 7 halves is. I'm sure that is a very nice number. Actually, I know it's a very nice number because we calculated it out before, and we said that this is going to be, what do we end up with? This was 243 all divided by 7. The part of the 9 went into this thing to cancel out some of this stuff here. So I put that in my handy dandy calculator. 243 over 7. This is equal to x squared integral times f of x. This is e of x squared. Okay, now what was standard deviation? Standard deviation is e of x squared minus e of x squared. Okay, it's an easy way to remember it. So we go over here and we say, okay, well, this was 243 over 7 minus, again, we worked this out before, and what was my average? It was 27 fifths squared. Okay, so as delightful as that is, we end up with doing a fraction problem, so 243 over 7 minus, and then when I type this in the calculator, we ended up with 729 over 25. Okay, when we did this arithmetic, this was 972 over 75, over 175, over 75, over 175. Okay, this is sigma squared. This is my variance. Okay, so that's how we're figuring that out. When I took the square root of this thing, and I can't do that in fractions anymore, I ended up with 2.36. That was my standard deviation, 2 decimal places. Okay, my average, going back to my average, was 5.4. This was my average. Okay, so parts A and B were okay here. We have part A, we have part B. All right, the next thing that we really wanted to figure out, we wanted to know what the chances were that we were going to be bigger than the average. Okay, so what is the probability? Okay, going to the next page here. What is the probability that x is greater than 5.4? So this is just an integral. We're going to go for 5.4 all the way up to 9 of 1/18 times x to the 1/2 power, right? That was the original function. And we're just going to do this integral. I'm going to go ahead and say, you know what? I would like to do what f of x is, and that's just what the integral, just the basic integral of 1 over 18 x to the 1/2 is, because I want to know what this value is. I'll show you a little trick here. This is equal to 1 over 18 x to the 3/2 times 2/3. We can go ahead and deal with this. So this is just going to be 1 over 27. The 2's cancel. So that's going to be 9 times 3 is 27. X to the 3/2. This is called capital F of x. This is the cumulative. This is the cumulative distribution. Okay, the density function we haven't integrated yet. The cumulative distribution, we have now integrated it. And in order to figure out probabilities here, I'm going to say F capital F of 9 minus capital F of 5.4. And that's going to be the probability that x is greater than my 5.4. Okay, so we ended up with, when I typed in 9 here, I got a 1. Okay. And then I typed in 5.4. I got 0.4648 to 4 decimal places. For reasons of the 1950s, and 40s, and 30s, we used to use these things called CRC books. If you are biology and chemistry, you probably deal with those a lot because they have a lot of physical constants in them. And almost always they are out to 4 decimal places. Therefore, almost everything we do numerically in math classes is out to 4 decimal places to align with the fact that we used to have to look all these things up in CRC books, and we're just going to make sure that they all look the same. So we went through and calculated this, and I got 0.5352. Okay, this is the probability that if you throw a dart at this value, going way back up here for a moment, right? Here's 9. Okay, what was my average? It was 5.4, so it's 5.4 here. If I threw a dart at this picture, then there is a more than half the chance, I didn't draw it that way, but there's more than half a chance it ends up in this region. Okay, and that's just the way that tends to go. Okay, so that makes sense. Just drawing like kind of a little picture to see what goes on with that. What is the probability? We are between one standard deviation of the mean. We are within one standard deviation of the mean. We are within one standard deviation of mean. Okay, so what we're going to do is we're going to go back to our mean and our standard deviation. I'm going to say, okay, I need 5.4 minus, what was my standard deviation? 2.36. And then we're going to say 5.4 plus 2.36. What does this equal? What does that equal? Fortunately, I have already done this problem, so I will tell you. It'd be nice if I could have written them down somewhere, but they're right here. I got 3.04 here, again, to 2 decimal places, and 7.76 for this one. In order to figure out the probability there between the two means, we're just going to take f of 7.76 minus capital F of 3.04 and just do this arithmetic problem. Okay, so that's all we're going to do with this. And we've got, okay, when I calculated all of this out, we ended up with, I think, 1/27 times both of these guys. This was 7.76 raised to the 3/2 power minus 3.04 raised to the 3/2 power, because we're already just figuring this out. Okay, because remember it was 1/2, we added it. So we ended up with this. So I ended up with 1/27. This thing was a delightful, I think the whole thing was 16.32. And when I calculated 16.32/27, I got 0.604. Okay, so again, if I go all the way back up here to my picture and I look at my value, I'm looking at my mean, and we are trying to throw a dart and hit this picture somewhere between these two squiggly lines. Okay, but that's what we're trying to do with all of this. Okay, and again, calculate out the whole thing, figure out your capital F of X, and it's a much easier problem. You don't have to keep doing integral after integral after integral. Okay, that's not a fun thing to have to deal with. Okay, the next problem was figuring out where the median was. Okay, so where is the median? Okay, so we're going to say, okay, we have got 0 to m, as opposed to going all the way up to 9, of f of x, and this is going to equal 0.5 or 1/2, whichever is convenient for you. So when I did this, we integrated out this thing. I got capital F of m minus capital F of 0 equals 1/2. Well, capital F of 0 was just 0. So capital F of m, we got 1/27 m to the 3/2 power. That was the integral that we had from way back up there, is equal to 1/2. Okay. And then this is going to be m raised to the 3/2 power equals 27 halves. And going back to our algebra class, we undo this by raising both sides to the 2/3. And we have our median is equal to 27 halves raised to the 2/3 power. Okay. And I ended up with my median was 5.67. That means half the probability is before 5.67, half the probability is after 5.67. And that would be the median. That's how we figure that out. Okay, so I will do more examples, but I think that is plenty for this particular video. So I'm going to go ahead and let that go for that. Thank you very much for watching the video. I hope this was everything you wanted it to be for both probability and statistics and for calculus. Okay, so very good. Happy studying, and I will see you in the next video. All right, take care.